Bonjour tout le monde, je m'appelle Raphael and aujourd'hui je vais parler de trois structures de données probabilistic, and that's all my French that I have today. Let me switch back to English. So today I'm going to be talking about three different probabilistic data structures: the count mean sketch, the Bloom filter, and TopK, all right? I like to start my presentations always with a little bit of context, a little bit of history, a story of how we got to it today and why we're implementing together what we're going to be implementing together today, all right? And today's not going to be any different, and the story of today actually has two protagonists. One of them you're pretty much very familiar with. It's Elon Musk, the guy on the left, and the other one, unless there are Brazilians in the audience, I don't think so, nobody's going to know him. But this is Alexandre de Moraes. He's one of the judges of the Supreme Court of Brazil, all right? And in August of the last year, what happened is that oh, too fast here. Alexandre de Moraes, through the Supreme Court of Brazil, he requested that Twitter banished a couple of accounts in secrecy, all right? Twitter didn't do so, and after that, Alexandre de Moraes, through the Supreme Court again, threatened to arrest the legal representative of Twitter in Brazil. Elon Musk didn't like it, so he stopped the operations of Twitter in Brazil. He closed the offices, and he let go the employees that they had in Brazil. However, according to the Brazilian laws, that's illegal. So Alexandre de Moraes summoned Elon Musk through Twitter, through the Supreme Court, of course, and asked him to appoint a legal representative to Twitter in under 24 hours. If he didn't do so, then Twitter would be suspended from Brazil. He didn't do so, and on the 31st of August, Twitter was suspended from Brazil. And actually, that part of the story is not the most interesting for me. I'm not even sure if I gave out all the facts correctly to you, so if you're interested in that part, I suggest that you go and do your own research. Otherwise, I might be spreading some fake news, and I don't want you to do that, all right? What I want to talk about is actually the consequence of what happened, because on the following day, Bluesky got 1 million new users. So we had all of those Brazilians who were on Twitter trying to find a new platform to go to. Some of them went to Threads, some of them went to Mastodon, but a lot of them also went to Bluesky. Is anybody on Bluesky here? A couple of people. Oh, all right, that's a lot, that's good. I'm also there. If you want to follow me there, I can follow back, all right? And then you can talk and communicate, that's cool. But you can see that Bluesky also posted that thing on the 1st of September, saying, Brazil, you're setting new all-time highs for activity on Bluesky. And Bluesky is quite an interesting social network because it's actually decentralized. It runs under the AT protocol. And the AT protocol is pretty much, in a very roughly explanation, like emails. So basically, you can have your email on Gmail, for example, and still communicate with people who have their emails on Hotmail, all right? Because you all use the same protocol. And for Bluesky, that's the same thing. If your account is under Bluesky, this provider, you're not happy with it, you can always migrate your account to another provider or even host yourself and still communicate with everybody in the network. So Bluesky is not actually owned by any company, all right, in that sense. And it just gets cooler also because they offer a lot of REST APIs that allow you to interact with the social network in very fun ways. For example, you can search for posts without even authentication. You can re-like posts, reposts, follow accounts, all these kinds of things very easily through that REST APIs. But there's something even cooler, which is the firehose. And the firehose is what they call a WebSocket that they provide where you can listen to everything that is happening in the social network in real time. So new accounts being created, new posts being posted, people following each other, even people blocking each other because blockings are public in Bluesky. Right? You can listen to all of that in real time, and you can create very interesting tools out of that, analytic tools, bots, you name it, all right? And they also started providing, by the end of the last year, what they call the jet stream. And the jet stream is a, let's say, a smaller version of the firehose that is already filtered, and instead of sending the messages in binary format, it sends the messages as JSON, making it easier for hobbyists or even developers to parse those messages and play with them, basically, all right? And with that, the social network is still in its infancy, all right? So there are many things that they didn't have at the time that I created this presentation. One of them was videos, for example. Now they do have videos. You can upload videos. But they also didn't have a trending topic. They didn't have trending topics, basically, all right? And so I thought, maybe that would be cool if I could build my own trending topics for Bluesky, all right? And that's when you get to the actual presentation. So that was all the introduction to get here. So the original name of this presentation is Blooming Trending Topics in Bluesky, and you're going to do that with probabilistic data structures, all right? So how we're going to do that is by first listening to Bluesky's jet stream. Then you're going to parse each message and extract individual terms from that. We're going to filter noise, meaning that we're going to filter stop words from those messages. We're going to count these terms, and then you're going to sort them by frequency. And finally, we're going to detect spikes in their usage, meaning that we're going to detect the training topics themselves, all right? And the first thing we're going to do is actually listen to the jet stream. And that can easily be done by using Spring WebSocket. Has anybody worked with Spring WebSocket before? Nobody? All right, a couple of hands. So basically, you can just plug it in to your Spring Boot application, and then you can, let me see if that works. Oh, yeah, it does. That's my first time using that clicker. Fancy, huh? So basically, you can define a class like JetStream client, annotate that with client endpoint, and then implement those methods such as onOpen, onMessage, and onClose. And whenever you get a message, it's going to use that method and the behavior that is implemented inside of this method to treat the message. Right? So that's how we're going to listen to the JetStream WebSocket. Fairly easy. And then we're going to parse those messages, split them into words, clean them by removing punctuation and symbols, and finally count the number of times each word shows up in this data stream, basically. All right? And to do so, the first thing that I thought was by using a sorted set. So does everybody know what a sorted set is? Could you raise your hands if you do? All right, so a sorted set is pretty much like a set, but alongside each member in the set, you have a counter or a score, basically, that in this case, we're going to use as a counter. All right, so you can see that you have the words here, such as life, bad, art, and then the counting of each of these words next to them. However, the problem is that I told you that I wanted to also detect the spikes, right? And to detect the spikes, I would have to keep historical data of these frequencies, meaning that for 1 minute of data, I would need a sorted set with approximately 22,000 members, all right, which would be translated into 2 megabytes. And even though sorted sets are efficient, in 1 year, it could be translated to 1 terabyte. And in 1 day, it could be translated to 2.8 gigabytes. It's a lot of memory, especially for me, who was doing that on my own as an individual with my own resources, right? But even for companies, depending on how huge those data streams might be, it might be expensive to keep a lot of data, as you're going to see later, all right? And by the same time, I was actually doing my interview at Redis. So I was talking to the person who was going to become my manager later on. And he asked me, do you know what probabilistic data structures are? And I said, no. And then he said, good for you, because you have to prepare a presentation about it for your interview. And I said, I would prefer not to. No, just kidding, I didn't say that. That's why I'm here, because I presented. So that's basically an enhanced version of that presentation that I presented to my manager at the time. But before we jump into probabilistic data structures, let's remember what are deterministic data structures, all right? Because deterministic data structures are those data structures that you work with every day. So basically, maps, trees, stacks, lists, and they're called deterministic because you know that anything you insert into them, you're going to be able to extract back later on. So for example, if you're using a list and insert an element to a list, when you iterate over this list later on, you'll know that your element's going to be inside of this list. And that's not actually true for probabilistic data structures. So if we're talking about a Bloom filter, for example, that behaves similarly to a set, when you add a member to a Bloom filter, and then you try to fetch it back, you're gonna get it back. However, it's gonna say that it has been added to the filter. However, it might be that you try to check if something has been added and this thing hasn't been added, and then you get a false positive, right? You're gonna see that all in details later on. But probabilistic data structures, they're not deterministic as their name actually says. All right, so the first probabilistic data structure you're gonna be looking at is called count, mean, sketch. So a count, mean, sketch is used for estimating frequency. Basically, we're gonna use it for counting, all right? And it operates with space efficiency, meaning that once the CMS is initialized, it's going to have the same size forever, independently of how many members you add to it. So if you're counting 1,000 elements or 1 million elements, it's going to keep the same size as it had when it was initialized. basically. All right? And what we're trading off is a little bit of accuracy that you're going to see that we can control how much of that accuracy we're giving up to get the speed and efficiency in terms of memory that it might give us. All right? And let's, oh, what's that? Oh, sorry, guys, he likes the attention. Let me clean that off. All right? So basically, that was the perfect data structure for my use case, because instead of storing 1 terabyte of data per year, I could store much less, as you're going to see later on. All right, so let's see how a count-min sketch actually works. So basically, when you initialize a count-min sketch, you're going to have a grid, or a sketch, or a matrix, or a bidimensional array, whatever you call it, of fixed size. So basically, going to tell, OK, I want a count-min sketch of, let's say in this case, 5, with a length of 5, and a depth of 3. And it has a fixed size. Once it's initialized, it's going to be of this size forever. All right, and then let's see what happens when you try to count elements with the CMS. So to do so, we're going to create a command, which is the cms.increby. We're going to pass the name of the CMS, which is terms, and then you're going to say what we're trying to count, in this case, Redis, and the number of times you want to count it. Let's issue this command to Redis, and what Redis is going to do is, for each row of this CMS, it's going to use a different hashing function that is deterministic, and that is always going to return the same number. So let's see. For example, for the first row, it's going to hash the string Redis. And as you can see, in my example here, it returned 2, meaning that we're going to increment the counter in the second column of the first row. Let's see it happening in real time. OK, perfect. And then it's going to repeat this process another 2 times in our case here. And for the second one, it's going to store in the 5th column of the second row, increment the counter there. And for the third one, it's going to do that on the second column of the 3rd row. So let's increment the counter there as well. Now let's add a couple of more terms to our CMS. For example, pets. We're going to increment this counter as well. And what Redis is going to do is it's going to hash the term pets. And we're going to repeat the process. In this case, it returns 0 for the first one. So we're going to increment the counter in the first slot of the CMS. Right? For the second one, we're going to increment the counter on the 4th column of the second row. And finally, for the third one, we're going to increment the counter of the second column of the 3rd row. But you can see that the counter here had already been incremented before. And in fact, it's going to be incremented once again. So now it says 2 there. All right? So this slot is being actually shared by multiple elements in the CMS. And you're going to see what's going to happen after. Right? But let's keep incrementing counters inside of our CMS. So let's add another one, which is cats. OK, so it's going to increment the 4th column of the first row. And then it's going to increment the last column of the second row, which has already been incremented before. So it's going to become 2 now. And finally, we're going to increment the first column of the last row. Right? And just one more before I actually show you how we can query elements back from the CMS. Let's add dogs now. All right? Let's issue this command, repeat the process. So we're going to increment the 3rd one. So we had another hash collision there. All right? And then we're going to increment the 2nd column of the 2nd row. And finally, we're going to increment the 4th column of the 3rd row. Right? Now let's try to query something back. So let's try to query dogs back. Let's ask the CMS how many dogs have been counted. All right? And what we're going to do is we're going to repeat the same process. But instead of increment the counters, we're just going to look at what's stored in each of these slots. All right? So the first one is going to return 2. It all happens under the hood. All right? The second one is going to return 1. And the third one is also going to return 1. And here's the catch. That's why it's called count-min sketch, because we're going to look at the minimum value that has been retrieved so far. And this one is 1, meaning that dogs has probably been counted only 1 time. And why am I saying probably? Because as you're going to see now, we're going to try to do the same for Redis. So we're going to ask how many Redis has shown up. And it's going to repeat the process. And it's going to return 2 for the first row, and 2 for the second row, and 2 for the third row as well. And the minimum here is 2, meaning that Redis has been counted probably 2 times, even though, in fact, we know that it has been counted only 1 time. Right? So that's why it's called a probabilistic data structure. However, we can control that error rate, all right, by defining the length, the width, and the depth of our counting sketch. So for 1 of 5 per 3, as we're looking at, you can see that we would have a 99.87% of confidence that the counter would be within 40% of the true value, all right? While if you had a sketch of 2,000 per 10, then you would have a confidence that 99.99% of the time, this counter would be within 0.1% of the true value, all right? And it's true, when you need precise countings, it might not be interesting to use that. But then you're dealing with huge data streams, let's say millions of elements, for example. If you get 1 million, or if you get 1,000,001,000, or 1,002,000, it doesn't really matter, right? Which is our case here. Okay, let's see how we can actually implement it. So going back to our JetStream client class, we had the onMessage function, and we're going to use that. For every message that we read, we're going to parse that message. Then we're going to clean those tags and split them into words. Then you're going to define the time bucket because I want to keep those, I want to count those per minute, all right? So I want to see which minute bucket we're looking at. And then I'm going to create the CMS for that bucket, ensure that it exists. And then for each word, we're going to basically increment its counter within the CMS, all right? And what I want to also do is I want to keep track of all the words that have ever been added to this CMS as well. Because the CMS, it's not going to hold the members themselves, all right? You're not going to know what's being added to that, what's being counted in that, all right? So I want to keep track of that alongside, but with a global variable, not one per minute, all right? And you're going to understand why later on as well. So let's see. I had the application running for a couple of minutes today. And I want to show you this other application. This is called Redis Insight. And this is basically a graphical user interface that you can use to look at what's inside of Redis. Let me see if I can zoom in that a little bit. Yeah, I can. That's good. All right, let me change the database here. So I'm looking at the counting sketch database. And for each CMS, I also created a sorted set so that I could compare them to you. All right, so you can see that for the sorted set, for example, of this one, let's say, of this minute bucket, all right, we had these words counted, and those were the most counted here. So you have the with 1,014 counts, basically, for that word, and then 2 with 647. But that's a sorted set, and you can see that this sorted set has 3 megabytes, all right? While the counting sketch itself has only 55 kilobytes, and we have 55 kilobytes forever, all right? But now let's see how close we are to those countings of the sorted set, right? So I'm gonna open the workbench here, and on the workbench, what I'm gonna do is, I'm gonna do query, and I'm gonna query not for the sorted set, but instead for the CMS, the word the. All right, let's see how many times it has been counted by the CMS, and it says 1,073 times. And if you remember, when you looked at the sorted set, it said that it had been counted 114 times. So it's not exact, that's why it's called probabilistic, all right, but it's good enough for our use case here. And we're saving a lot of memory. So that's what we're looking at. But what you're seeing as well is that you have a lot of words here, the, to, a, and, that don't actually have any meaning. So you want to filter those out, all right? And that's what we're going to be looking at right now. So let me go back to the presentation itself. Exactly. Yeah, that's.
You are asking how many times the word the is counted, but you don't know that which word are there.
Yeah, that's why I also created this set. Yeah, where I have all the words stored as well, so I can keep track of them later on. But it's a global one. All right. But I can answer all the questions in the end. Let me go back to the presentation itself. Okay, and now let's talk about filtering all the stop words out of this that we receive through the data ingestion that we're doing right here, right? And for doing so, we're going to use another probabilistic data structure that is called Bloom filter, all right? Has anybody heard of Bloom filters before? A couple of people. That's good. So a Bloom filter works very similarly to a set, all right? So basically, you can add members to the Bloom filter, and then you can test if those members have been added before to it. So basically, you can see if a word has been added to a Bloom filter or not, with some trade-offs. So basically, when a Bloom filter tells you that something has never been added to it, you can be 100% sure that it has never been added to it. However, if it says that something has been added to it, if it returns true, you cannot be sure that it's actually true. It might give you false positives, all right? However, you get, as I said before, the trade-off that you get the space efficiency, all right? So Google, for example, uses Bloom filters to see how, if the pages that they're trying to index have been indexed before. So they work with trillions of pages, even more than that. I don't know exactly the numbers, all right? So if they have to keep a set with all the pages they have ever indexed, it would be a huge set that would consume a lot of memory. So instead of doing that, they just use Bloom filters with a lot of algorithms and other checks around it, probably. All right, so let's see what we're going to do. Sorry, before that, let's see how it works. So a Bloom filter works similarly to a count min sketch, but it has only one, it's a one-dimensional array instead, all right? And inside of each slot, it's going to be initialized with a bit, which is a 0 first, okay? So let's see, of fixed size as well. It doesn't change the size in memory, all right? So, sorry. So let's see what happens when we add a new member to our Bloom filter. So let's create this command here, bf.add, and then the name of the Bloom filter, and then the word itself, I'm. Let's add it to it. And again, it's going to run some hash functions within Redis that are deterministic, that are always going to return the same number. And in this case, it returned 2, meaning that we're going to flip the bit in the third slot here. All right, so let's flip that bit. And let's do that the same thing 3 times. So the 5th bit here, let's flip it as well. And for the 3rd time, we're going to flip it on the 2nd slot. All right, now let's try to add something else, another member. And this time, we're adding LOL, another stop word. Right? And what we're going to see is that it's going to flip the bit in the 1st slot. And then it's going to flip the bit in the 4th slot. And finally, it's going to flip the bit in the 2nd slot that had already been flipped before. And in this case, we're not going to do anything. Right? You had a hash collision. We're not going to do anything. You're just going to keep it as it was. Right? Now, let's see if something exists inside of our Bloom filter. Right? So we're going to do that first with the bf.exist command. And we're going to check if I'm exists, that we know it does because it has been added before. All right? So what we're going to do is we're going to run the same hashing functions, and we're going to look at the bits that are returned. So it's going to return 1 every time. All right? So because we know it had been added before. And since all of them is 1, we know that this has probably been added before to our Bloom filter. All right? And let's see why it's probably later on. But first, let's check what happens when we try to see if devox has been added to our Bloom filter. And in this case, because I wanted to, because I created the examples, right, it's going to return 5 for the first hashing function, meaning that it's going to look at a 0 there, a bit that hasn't been flipped yet. Right? And for the second one, it's going to look at 1. And for the third one, it's also going to look at 1. But since one of them was 0, meaning that it has never been flipped before, we can be sure that this element has never been added to our Bloom filter before. All right? And finally, let's look what happens when you try to look at this other term, which is Brazil. And for this one, unfortunately, we're going to have hashing collisions all the time. So it's going to look at bits that have been flipped before. All right? And even though that data structure has never been added to our Bloom filter before, we're going to get a false positive saying that it had. Right? So that's the trade-off. When you get a no, we know that it's 100% true. When you get a yes, it might be true, it might not be. Okay? Let's see how we're going to implement that into our application. What we're going to do is we're going to initialize the Bloom filter when our application is started. And then we're going to read, or we're going to parse the JSON that I had already prepared, which is the stop words -en for English, stop words in English, JSON file. we're going to initialize the stop words Bloom filter, and I'm going to add all the words that are inside of this JSON inside of this Bloom filter. Okay? And now, on the onMessage function that we had seen before, we're just going to add an if in there, and you're going to check before counting a word if this word is part of this Bloom filter, and if it's not, then we're going to add it, and if it is, it means that it's a stop word. We're going to skip it. Right? And that's true. We might get some false positives, but given the magnitude of words that we have, it doesn't really matter for our use case right here and for many other use cases when you're dealing with huge data streams, all right, where speed and memory efficiency matters more than the precision here. Okay, so let's see. Let's look at Redis Insight one more time. Bloom filter, that's the database that I had prepared for you. So you can see that I have two. Let me zoom in. Yeah. I have two data structures here. The first one is the set, which is the stop words set. And on that one, you can see that we have this word site, list, merely, this, at, when you. All right? And we also have this other data structure that is a stop words dash bf. And what I want to do is I want to see if those words exist inside of our Bloom filter, all right? And I know that they had been added before, so they should return true. I had already run some examples here, so I'm just going to rerun them. So for the first one, for example, site, it returned 1, meaning that it probably has been added before, all right? For the word Brazil, for example, I know that it hasn't been added, so let's see what's going to return. It returns 0, all right? And since this is a demo with probabilistic data structures, I cannot really show you a false positive here because I don't know what would actually be hashed into something that would ended up in hash collisions that would give me a false positive here, all right? But if I tried with France, for example, it also said that it has never been included in this Bloom filter, and so on. Maybe if I had created a Bloom filter that was smaller, I would be able to show you the false positives. But I didn't do so. But what I wanted you to pay attention to is actually the sizes here, because the set with only 1,300 words has a size of 59 kilobytes, while the Bloom filter with the same number of members added to it has a size of 2 kilobytes, all right? So here we're talking about small data, that's true, but you can see that the size of the Bloom filter is significantly smaller than the one of the set itself. So if we're talking about huge data streams indexing trillions of websites, just like Google does, for example, or even if I was trying to see the ID of the posts that I'm indexing so I don't count the terms from a post that I had already seen before, then we would see even a bigger discrepancy here between the size of these data structures. All right, so that was the Bloom filter. And let's continue to the last part of our demo, which is basically detecting spikes. All right, so now we want to see what's actually trending in our trending topics application. And to do so, we're going to use the TopK, which is another probabilistic data structure that has basically the same benefits of the others. But this one, although it works a little bit like the CMS, it's used also for counting terms in, let's say, a data string. All right, it's actually going to keep the top K members of whatever it has seen before. So the top K can be 40, can be 30, can be 10 members. You define it when you initialize it. All right, and when it's initialized, it's going to have a fixed memory size that's never going to be increased, even though you try to count 300,000 different elements here. Let's see how it works. So basically, in this case, it has been created with a one-dimensional array of 5 slots. All right, so we're trying to count the top 5 elements of a data stream here. And what we're going to do is, before I say that, it also receives a decay, as you can see there, which is 0.9. All right, and you're going to be using that later, as you're going to see. So let's try to add something, to count something with our TopK here. All right, so I'm going to create a command, which is the topk.incrby. The name of the TopK coming next to it, spiking now, and then the term that we're trying to count with the TopK, which is Redis here, and the number of times it's being counted. Let's issue this command to Redis. And what Redis is going to do is it's going to hash it one time, and then it's going to store the counter with the member alongside it in the slot that has been returned by the hashing function, right? In this case, the second slot. Let's add something else, count something else, actually. Let's count Devox now. We're going to repeat the process. It's also going to be hashed. It's also going to return a number. And then it's going to be stored in the position that has been returned here, right? So in the third slot here. But now let's see what happens when you try to count Java, right? Oh, sorry, let's increment devox one more time. It's important for the example. So it has been incremented to 2. And now let's see what happens when you try to count Java here. So let's hash Java. And we're going to see that it returned 2, meaning that it's going to fight for the third slot. It's going to fight with devox for that slot, right? And how it's going to do it? By using the decay that has been provided when you initialize that TopK. So basically what we're going to do is we're going to multiply the number of times devox has been counted by the decay, as you're going to see now, and then round that down. In that case, 2 times 0.9 is equals to 1.8, which rounded down is equals to 1, all right? So since devox is still greater than 0, it's not going to be deleted. In fact, Java is going to be discarded, and devox is going to be decremented in this case, all right? With the value that was returned from the decay multiplication there. Okay? Now let's try to count Java again and see what happens. So let's hash it. It's going to fight again for the same position. But now we're going to multiply 1 by 0.9, which is going to be returned as 0.9. And we're going to round that down, which is going to be 0, meaning that devox is going to be removed from that slot, and Java is going to take that place. Right? But if you think with me, actually, we still had 3 open slots here. So they're fighting for the same slot. That's the first thing. And the second thing is that devox had been counted twice, while Java had been counted twice, and Redis had been counted only once. And still, Redis and Java are in the TopK, while devox had been removed. And that's why it's a probabilistic data structure, because that's true. Some of the terms are going to be discarded, even though they were the ones that were the most mentioned, all right? The ones that show up the most in our TopK data structure. Okay, and now we also have the algorithm for detecting the spikes. So basically what I want to do is check the average frequency the words have been counted in the past 3 minutes, and then compare it with the current number of times that the same word has been counted in this current minute. All right, and then give it a score, and then use that score with our TopK. Let's see how we can do that. So to do so, I created a new function that is going to be annotated with a scheduled annotation, and that is going to be run every minute. And then I'm going to get the name of the key of each CMS of the current minute and the past 3 minutes. Then I'm going to get all the words that have ever shown up in our data set that has always been ingested by our application. So answering your question here again, we have tracked those words, all right, but in a single set here. Then you're going to create a TopK if it doesn't exist, which is going to be the spiking dash TopK, which is, in this case of the example, is 40, but in my demo, it's only 10, so it's a top 10. Basically with the decay of 0.9, as you can see there. And finally, we're going to calculate the average. And if the average is greater than 0, meaning that it has been counted through those counting sketches before, we're going to actually calculate a spike score and then count that score with our TopK data structure that we had created previously. All right, so let's see that in Redis Insight now. Let me go back to Redis Insight. I have a third database here, which is the TopK. And here I have these 2 data structures. The first one is the spiking now, and the second one is the spiking TopK. All right, and you can see that for the spiking now, I have, oops, sorry about that. I have added 60,000 elements to it, and you can see that the ones that have shown the most are those one here. So those that have the highest score, meaning that they are the ones that are training the most. So love, Agravitas L, people, Wubble, Rocket.com, story, friends stay, and so on. And what I want to do is I want to go back to the Redis command line interface, and I want to run these 2 commands here. So the first one is for displaying the top 10 from our sorted set, as we just saw. And those are the words that were returned. And the second one that I'm going to run is to list the elements from the TopK, so we can compare them, right? And let me just move that up, zooming a little bit. Oh, didn't work. But you can see that the TopK basically is returning almost all the words that are being returned by the sorted set as well. So we have love as the first one, Agravitas L, people, Wobble Rocketcom. Even though we have followed the frequency or the scores of more than 60,000 elements with the TopK, all right? It kept only the 10 ones with the highest scores, and they're still pretty much the same as the sorted set. We still have, for example, American in the sorted set is at the 11th position, but in the TopK is in the 9th position, so we have some discrepancies. However, for trending topics, it's still good enough. All right. Oh, I forgot to show you that. Most important part. That is that the sorted set has 6 megabytes for 60,000 elements, and the TopK has 284 kilobytes for basically keeping track of the frequency of the same number of elements. Of the spikes, actually. Sorry. Let me go back here. Okay. So that's pretty much what I had to show for you today. And what we can see here in the end is that the memory used by using probabilistic data structures was much inferior than the memory used by using deterministic data structures. Let me try to use that again. So you can see that for probabilistic data structures, in 1 month, we would have used 2.34 gigabytes of memory, while for the deterministic ones, we would have used 87 gigabytes of memory. Right? So much less memory, while keeping track of roughly the same data. That's pretty much it. If you guys are around on Friday, I'm also going to be presenting on Friday. I'm going to be talking about vector similarity search using the data of the Apollo 11 mission. So if you guys are around, please come by to see it. And finally, let me present myself. My name is Raphael. I work as a developer advocate for Redis. I've been working there for the past 6 months. Before that, I worked as a software engineer for the past 8 years with mostly Java and Kotlin. I also have a YouTube channel where I share a lot of videos about Redis. And I also post videos on the Redis YouTube channel. And on this QR code, you can find all my socials and also the demo for this application. You can run it yourself in your computer, and the slides as well, and everything else you might imagine. Thank you very much. You guys have any questions? Still have 7 minutes.
Can you comment on at which point, like how do these work? Do they still work if you have more stable distribution, like more flat distribution, as opposed to very skewed distribution where a few of the elements have most of the counts and that kind of thing?
Yeah, so basically that depends on the detection of spikes algorithm that you use. All right, that one I used a very simple one where I'm basically counting the average of how many words have been counted in the past 3 minutes and comparing to the current one. But it's not really related to the data structures itself. It's more related to how you implement those algorithms. All right, so the data structures are just giving support to keeping track of those frequencies.
Okay, but it seems to me that the data structures, like if I feed them a well-balanced stream of words, and like there's around the same count for every word, like they're going to, it increases the chance that I get a non-conclusive data out of them, doesn't it?
That's an interesting
like
question.
It fully works for this case specifically, but what I'm trying to get at is, does this still work in cases where my data is more flat?
So basically you're saying that you have
flatter distribution.
So basically you're saying that the count of words would be the same, basically.
Or around the same, not necessarily precisely the same, but I imagine that like words like the a, even though like ignoring the fact that you remove them, are very, very present in a lot of messages. But if they were more close together, those data structure lose in
Yeah, in this case, you would have to have a very good algorithm for detecting the spikes and giving a score that is more discrepant between them. Right? Because basically you're the one that is defining the score among those words. You see, so you can actually increase the distance if those are very close by. Thank you.
Hello.
Hi.
Could you please show the sizes of the data structures that you used?
Yes. Those?
And so I see the biggest discrepancies for the counting words.
Yes.
Is it a quirk of the data that you used from Bluesky, or because I see, like, for example, filtering stop terms, it goes from 60 kilobytes to 2 kilobytes. Counting words goes from 90 gigabytes to 2 gigabytes, so it's around about the same ratio.
Yes.
But as the data set will grow, will the ratio stay the same, or is one of the probabilistic ones much better and grows much slower than the deterministic ones, or they're all around about the same? Because, for example, also ranking spikes, it's like also like it's the one that is 10,000 times less, for example, than the other ones. So it's all like, does the ratio stay the same, or do they grow differently?
No, the thing here is that for the counting of words, I create a bucket for every minute.
Oh, okay, so it
Right.
stays the same.
So we have many more sorted sets in that case, and that's why we have so much data for counting words in this case.
But if the number of users is much greater and the number of words in total per minute is greater, is the ratio between the sizes of the deterministic and probabilistic data structures, is it going to stay the same? Because, for example, we see that counting words, it's a big data structure, but maybe if it was smaller, it wouldn't be as good as the other ones. I'm very new to this, so I would like to know, because
yeah, that's true. If it was smaller, it wouldn't have saved as much memory as it has saved. So basically, the sorted sets are very big because of the size of the streaming, of the size of the words we're counting.
Thank you.
More questions? All right. Thank you very much. Enjoy the rest of your day. Merci, actually. Sorry.